Have a go at this, see what you think. So we're talking about timeouts last time. So technically we started the lecture and started recording. And see what you think. So I don't know if you remember the formula. So this is, you're going to do this as part of Wireshark, which is, this was the formula we used, right? I'm not going that bad. I'm only like a lecture behind, so it's not a big deal. But rather go slow. I can go fast. Probably to your detriment. So this is the kind of thing we talked about. A really important thing is how to estimate the timeout. How do you get a good value? Because that value can directly affect performance, right? So the question is really trying to say, so the alpha there is x, by the way, in that question. So when calculating RTT in TCP, we weight the contribution of the current estimate and the new sample. The optimal choice of alpha depends on the characteristic of the network. For what type of traffic would a large, that means, setting that value to 1 be appropriate? Have a quick think. Give you a minute or two. Eight submissions. We lost a lot of people along the way. Somebody asked me a question last on Monday, right, at the end of the lecture about this. And we had a deep and meaningful discussion. So I thought I'd post it. Eight, come on. What do you think setting alpha to 1? What would happen if you set alpha to 1? In this equation, what would happen? If this was 1, then that term would disappear, right? So the estimated RTT will depend on what? Your current sample, right? Think of another scenario. What would happen if the round trip time was 100% perfect all the time? It was 10 milliseconds every single time. What would you set the alpha value to now? What if you had a perfect network and you always got the same alpha value? Sorry, you got this. What would you set the alpha value to then? 1 or 0. Okay. So you have, so you got one estimated sample RTT is 10 milliseconds, the next one is 100, other one is 5, next one is, I don't know, 50, 300. It was continuously fluctuating, and the RTTs were not related, right? That would be one extreme case. What would you set the alpha value to then? 21 submissions. Let's have a look at what you guys think. Okay. That's kind of interesting. So, let's think about the case where this guy is constantly changing, right? All the time. Okay? So every sample is unrelated to the previous one, and it's jumping around a lot. 500, 2, 0, I don't know, 1, 500 milliseconds. Doesn't matter what you set alpha to and what your estimated RTT is. Or another question is, can you estimate the RTT? If this was always jumping around and had no relationship to the values that you get, one after another, could you estimate the RTT? No, it's difficult, right? Whatever value you set is going to be wrong, right? Who knows? Yeah? Do you get that? So I guess the point of this exercise is to what you're trying to do is essentially think about what would be a good value for the timeout in the future, right? Based on what you've seen. But if what you've seen has no relationship, then this, whatever value you set, this is not going to work, right? Okay? So if you think about the other extreme case, where you have a perfect network, every single measurement is 20 milliseconds, right? Every time is 20 milliseconds. Now does it matter what value you set alpha to? Every sample RTT is perfect number. Does it matter what value you set alpha to? What would you set alpha to now? Does it matter? Friday blues, you guys are feeling cold? Shall I turn the air conditioner off? I'm feeling cold. Does it matter? Doesn't matter. Yeah, it doesn't matter, right? It's fixed, right? It doesn't really matter what value you pick alpha to, because eventually you get the right answer, and then you'll just continue, right? So the value of alpha is really something that's appropriate between those two extremes, right? When the network is crazy and you can't predict versus network is completely stable, reality is something in between, right? So yeah, just a thought exercise in terms of thinking about what might be a good value for alpha. So you can see most of the time it's about 0.1 is what's chosen, right? As to calculate the estimate RT. So just recalling, what is the influence of alpha and why would you set it to a certain value, and what effect that has. And the purpose for doing this whole thing is to be able to estimate a future value based on the past values, right? And if you can't do that, then there's no point looking at the sample value. So going back to what we were talking about is essentially looking at TCP. Sorry? Nothing. It depends. Yeah. So
What does the estimated RTT start at?
Yeah, that's a good question. So I think it starts at like 1 or something small, maybe like a millisecond. So I have to look at the spec to tell you exactly what typically it starts off at. Yeah, it's a good point too. So you got to start somewhere, right? It could be your first sample. Could be the way you initialize the algorithm. Yeah. Two good questions. Coming back to what we were talking about. Okay, so my aim is to finish congestion today before I go. Then I will feel happier. So we talked about sequence numbers and relationship between sequence numbers and window size in terms of receiver. We looked at flow control. If you remember flow control, just a quick slide, right? This is about not overwhelming the receiver and telling and letting the sender know how much spare space you have in your buffer. And the question that I discussed last time, right at the end, was about what would happen if you send a packet back, an acknowledgement back, with the receiver window size set to 0. Recall that the TCP protocol has a header field called receive window size, which it uses to inform the sender about how much space you have in your buffer, right? Put stuff into. So what if you set this to 0? So essentially what would happen is the sender would quench. It would stop sending. So how would the sender know when to start sending again? That was my question to you, right? Okay, so you got an acknowledgement saying, I've got no space. Technically what I should do is stop sending. So what do I do, right? So right at the end, we had a bunch of ideas, and just summarizing from memory was having some kind of timeout. So the sender would go, well, I'll wait for a timeout period, then try sending something. Then, what kind of packet do I send, right? Do I resend my last packet, right? Do I send a new packet of data, right? What do I do? So that was kind of where I left off. If you were to retransmit the last packet, and your last packet was 1,500 bytes, and then your receiver was still full, right? Would that be a useful thing to do? No, why not? It's because what do you waste in terms of, it is cold in here, right? What do you waste? Because you could be timing out and sending this packet, but your receiver's still no buffer space left, right? You waste what? You waste bandwidth, right? So, so you could potentially retransmit the last packet, but if your last packet had a large payload and your receiver was still full, you end up wasting bandwidth. So the decision that TCP has made is to actually send a packet back with a single byte, right? Okay, sends a packet with a single byte to test if it gets accepted, right? So remember that sender and receiver, the discussion forum post about the tutorial question was that essentially when you make a connection, you have a byte stream between a sender and receiver, right? So you're sending bytes across, and you're keeping track of how many bytes you're sending, which is essentially what the sequence numbers do, right? So when you stop sending bytes because you can't, the receiver is full, then you just send one byte at a time to check, right? So it's a small cost to pay, right? You're sending a single byte to check if the receiver can receive that byte. If it can, then you start increasing, right? Because depending on what the receiver window size is on your acknowledgement, okay? So the decision that TCP has made, right or wrong, there's many ways to solve the problem, is to send a byte with send a single byte payload packet to the receiver to check if you get an acknowledgement back with a window size obviously greater than 1, right? Okay. So just finish. Do you have any questions about flow control? How that worked, and the problem we talked about, and different solutions versus the solution that TCP picked? Good? Okay. So the next part I want to talk about is before connection. I think we're going to jump here, right? Connection establishment and termination. Then we do avoid congestion at the end. So I roughly alluded to this when we talk about HTTP, and then if you guys had your tutor already, so you would have you may have come across the three-way handshake, right? In terms of talking about why HTTP uses pipelining. Okay. Just recall that when we started talking about the application layer protocol, we had a diagram like this, right? So between a client and a server, I said you send a packet to establish a connection, then you get a response back, right? And then you send another one, right? So this is you send your request, and then you get your response. This is just going back to HTTP and what you would have talked about in your tutes, right? So we talked about having two RTT. Do you remember when we talked about HTTP? Yeah? So this is where the two RTT comes from. So it actually comes from the way that you make a TCP connection, right? So this is the HTTP request, by the way. Okay. So it's called a three-way handshake. There's a good reason for that. Let me give you an analogy, a good analogy. Try to give you an analogy. So assume that you have you're climbing a mountain, and then you have somebody that's at the top, sitting here. Someone's at the bottom, and you've got a rope, right, that you've sent down, and the guy at the bottom needs to know if the guy at the top has tied the rope, right, so he's safe for him to climb. So, but they can't see each other, right? So the guy at the top can't see the guy at the bottom. All I see is a rope. I don't know if it's safe to climb up, right? So how they need to communicate the fact that the rope is now secure, right? So the method of communication is to just, wiggle the rope, right? So if the guy at the bottom wiggles the rope, and then the wiggle travels all the way up to the top, he goes, oh, okay, so I know the guy at the bottom is ready. So now the guy at the bottom doesn't know if your wiggle was received by the guy at the top. Are you following me? Do you want a diagram? No. Okay, so the guy at the top wiggles the rope. And then if that wiggle goes all the way to the bottom, the guy at the bottom knows, okay, he's got my wiggle, right? And then he's ready. But then the guy at the bottom, guy at the top doesn't know whether the guy at the bottom got his wiggle, right? Yeah. So the guy at the bottom needs to wiggle one more time, right? Okay. So the TCP handshake is a little bit like that, right? So the client says, I want to make a connection, and then the server says, okay, I've got your request, I'm going to acknowledge you. So the client now knows that the connection request was accepted, right? Yeah.
Is that actually protocol for climbers?
Protocol for climbers? Actually, might be. I don't know. I'm not a rock climber. I'd like to be. Probably not fit enough. Wouldn't be here lecturing. Yeah, there might be protocol for climbers. Maybe we just created one. So you have a request, a response. So that part confirms to the client that the connection request was accepted by the server, but the server doesn't really know if the client has received that, right? Okay. So for the server to know whether to keep that connection open, the client needs to send an acknowledgement. Okay. So now with this third message, both the client and the server knows that the connection is should be kept open and established, right? Connection established on the client side and connection established on the server side. Another way to think about this is think about why the third handshake is required. So you may send a SYN packet, and then it might get lost, right? So and then the client waits, sends another one, right? Okay, so maybe this one is either lost or delayed, and then the server accepts this connection, right? So replies to it. Okay, and the client assume that the client doesn't send an acknowledgement, and then eventually this goes to the server, right? And then because this got delayed and the server acknowledges that connection, but the client's already made a connection, right? So the server may end up with a half-open connection, right? Okay, so client has already established a connection from the first packet, but the second one, I already have a connection, so I ignore it, right? So what this packet allows this client to do in this case is that it can tell the server, look, I've already got a connection, right? I already got a connection. I can tell the server to reset this one, right? Okay. Say I don't need it. So you can close that. Don't keep this connection open. Close it, right? Otherwise the server is hanging, yeah, with a half-open connection. Okay. The same thing can happen with the CNA4 packet. Okay. What they mean is, okay, please, I want to make a connection. I acknowledge you that you're ready to make a connection, and then maybe this packet gets lost, right? Okay. Now the server may end up thinking, well, the client is ready for that connection, but the client hasn't received that yet. So the client may send another SYN request, right? So the server may end up with this dangling connection. No way of knowing whether it was established or not, right? So the whole reason that you have this three-way handshake is to make sure that when you have lost segments or lost acts, that both parties are able to determine which connections are live and which ones should be shut down. Okay? Then there's if you look at the protocol for establishing connection, I'm going to go look at, if you look at the packet headers, you'll see that a connection request is called a SYN packet. The reason for that is you set this flag called S here, right? So when I want to make a connection, I set this flag and send a packet, right? So this is a connection request. And you guys wrote your TCP web server a long time ago, so you had a welcome socket or server socket, depending on the programming language you used. It was Python, right? No, it was C. So that will be the connection establishment. Then when you establish a connection, what you do is, remember that TCP uses sequence numbers, and then the sequence numbers are picked by the server and the client for very good reasons. Security reasons are not the same, or neither are they zero, right? Okay, so they should ideally be picked randomly, right? So one thing you do is actually pick your initial sequence number and let the server know, right? And then the way the server acknowledges is by sending an ACK packet, right? So it's setting this flag, and then because it's a connection packet, so you set S and A and send what's called a SYN-ACK packet. So when you're using Wireshark, you will see a SYN, you should see a SYN-ACK packet that's coming back when a connection is accepted, right? And what the server is doing is also telling the client its sequence number, right? So you have the server side and the client side sequence numbers initialized. Okay. Now the acknowledgement should be, remember, it's the sequence number that you are expecting next. So the acknowledgement field will have a sequence number which is one more than the one that you got, right? Remember in TCP, you always acknowledge the thing that you are expecting next, okay? And then from a client side, finally to acknowledge, you send back your sequence number, which should be this one, because this is the next packet, next byte that you're sending after x plus 1. And then in your acknowledgement, you should have the packet that you're expecting from the server, which is y plus 1. Okay, right? Now, when I talked about HTTP, what happens really is that, so this part is your connection establishment, right? Same as that. And then what really happens is that in your CNAC packet that you send, what you do is you actually piggyback, for example, an HTTP request. So that becomes that one, right? So your acknowledgement to the server can also carry the payload for HTTP, right? So that's how you get that one, okay? And then you get a response back, right? That's how you end up with two RTTs for HTTP 1.0, right? So you get your SYN, SYNAC, and then you get a SYNAC piggyback with a request and response, right? That satisfies a single HTTP request, okay? So that's how I got to 2RTT when we were talking about that problem, and now we have some insight as to why that is the case. Is it clear that to you guys that we need the third ACK and that two-way handshake is not good enough, right? So if not, think about that and then come and have a chat with me if it's not clear that 2 is not enough, okay? Cool. Because TCP is connection-oriented, so we also have to tear down that connection. So once you establish the byte stream, then we need to tear it down. If you don't, both parties maintain state for that connection, and then eventually, if you have too many connections open, you may have come across in your life that machines run out of resources, right, and stop accepting connections. So how does a teardown work, right? So teardown, another motivating example for the teardown, it's different to the mountain climbers. So this is a famous problem. Maybe you've seen it in computer science already, the Byzantine generals problem, it's called. So essentially, you've got two armies. Who's trying to attack this army in the middle? The red army. And if only one side attacks first, they're going to be overwhelmed. 3 is more than 2, and they will die. So the only way to really defeat these guys is for both of these parties to coordinate their attack simultaneously and descend down into the valley. But these two guys can't see each other and have no way of communicating with each other, right? So how do you coordinate an attack? Got any ideas? This is essentially what you have to do when you have to tear down a connection. You have a client and a server who can't see each other, right? Okay? And they need to coordinate themselves so they can tear down the connection, right? Yeah, smoke signals, right? Smoke signals. Well, smoke signals, yeah, possible. I mean, we could send smoke signals too, so reliable, may not be reliable. I could fool these guys. So say attack at dawn, and we might go, we change our mind, attack at sunset from the middle. Yeah, smoke signals. Any other ideas? How could two parties coordinate when they can't see each other and don't have any modern telephones and GPS? What?
Can they agree on a time beforehand when they're gonna?
Yeah, that is possible. So, but they came from two different lands, traveled across the seas. There was no way to meet. They never seen each other, right? I don't know. This is your allies or whatever. I guess I don't want to spend too long because I want to get through the lecture. But the point is there's really no good solution, right? There's no good solution. So if you have a brilliant solution, well, that would be yeah, we should write a paper. So given those conditions for that problem, there isn't really any neat solution to it. So what that means is that in terms of TCP teardown, when you have two parties who can't see each other, who's never met before, you could say, oh, well, I'm going to only maintain the connection for 5 minutes, but you don't know, right? You could say, what if you want to use it for longer? So it's not really a perfect solution in terms of client and server, right? So it's really there isn't an elegant solution, but you got to come up with something that works most of the time. So which is what TCP tries to do, right? So in terms of terminating a connection, come up with a protocol that works most of the time well. And the way that works is very similar to the three-way handshake. So when you're trying to terminate a connection, what the client does is it issues what's called a FIN. That means I want to terminate, right? Packet. So if you look at the TCP header, you'll see that there's an F flag here. Okay? So you send a packet with the F flag set, which is just to let the server know that I want to terminate my connection, right? And then from a server side, the server acknowledges the client that, okay, right? I've got the fact that you want to terminate a connection. So now client is pretty much, in terms of the client's point of view, I'm done, right? I told you I want to terminate the connection, I'm done. I could just close my connection, release my resources, and go away, right? But the client doesn't do that, right? Client doesn't do that. What it does is it goes into what's called a timed wait period, okay? It doesn't just close this connection and release its resources, but it goes into a timed wait period. Why does it do that? Why does it need to do that? What could happen? Why doesn't the client just go, yep, okay, I told you I wanted to terminate, you said you got it, I'm done, gonna go away. Why doesn't the client do that?
Because the server doesn't know that they've received the packet.
Yeah, that's right. Server doesn't really know what happened. Okay, this could have gotten lost, right? So it's possible that one of these parties may end up with a half-open connection, right? Okay, the server doesn't really know the ACK packet was received, right? And this may have gotten lost. So because we have this problem with corrupt packets and packets getting lost, you could have a case where you have one of the parties with a half-open connection, the other one with a closed connection, right? So the way to do that, to be nice to each other, right, is for the client to actually go for a wait period to increase its chance of finding out if the server has actually got the ACK packet and it's also ready to close, right? So I've got my ACK packet and the server says, okay, I'm going to now close the connection, right? I'm ready. So I get a FIN packet, I send a FIN packet, and then if this packet is lost, because I'm going to wait for a while, right? Hopefully this server will retransmit, right? Then I will get it, okay? And when I get it, I send an ACK back to let the server know, yep, I know you told me you're ready to tear down your connection. I acknowledge it, right? So that's saying I've sent everything I need to send. I'm ready. You're ready. Let's both tear down the connection together, right? So coming back again, so just the client telling the server that it's done, things can go wrong because packets can get lost. So what the client does is actually goes into what's called a timed wait period to know that the server is also ready to tear down the connection and has done so, right? Look, it's possible that within this timed wait period that this FIN packet got lost and I've just tear down the connection and then the server has a half-open connection on its side. It's possible that can happen. And in that case, there are ways, mechanisms like timeouts that the server can use to see if a connection is idle, and then eventually it'll clean it up, right? But that might take a lot longer than you'd like. So ideally what you want to do is for both parties to be able to close that connection down gracefully, right? First party and the second party, and both parties to acknowledge that they're ready to do so, okay? Typically what happens when you guys are using Wireshark for this stuff is you might find that just like in the three-way handshake, that these two are actually sending the same packet, right? So what you might see is a FINAC, if you like, right, sent together, okay, as opposed to 4 messages. So you might just get both the F flag and the A flag set. So don't be surprised if you see that. That's typically how a teardown happens. So you send a fin packets, I'm ready to close. Then you send a ACK and a fin to say, yep, I'm ready to close. And if you don't get that, then if this gets lost for some chance and you retransmit, because the client is on a timed wait period, the client has an opportunity to send the ACK back, right? Okay, yeah. So eventually, hopefully in one of those situations, the client is still up and sends an ACK back and the server goes, yeah, okay, I know you've closed, now I've closed, we both acknowledge each other, right? So this is how the 2 armies synchronize themselves to close down a connection gracefully, right? By using this protocol, okay? Any questions on that? Cool, fun stuff, all right. The last thing I'm going to talk about is congestion, right? Congestion avoidance. So this is going to close our chapter on TCP, right? It's a long, long chapter. Probably the bulk of the course between TCP and Internet Protocol, which is coming next. So congestion avoidance is really, really important. Why? Because we've all experienced it. Ever found the network to be slow? Yes. Yeah, all the time, right? Why is that? Chances are there's congestion along the trunks that you're sending data in. So motivating example, let's say you have there's things called routers in the network, which we're going to look at later, but essentially their job is to look at the stuff that's coming in and determine which outgoing link to use in terms of sending it to its destination, sending those packets to its destination, right? So what could happen is if this is a rate and this is a rate, let's say this is, 100 packets per second, and let's say this is another 100 packets per second arrival rate, and then let's say your outgoing rate is only 100 packets per second, we have a problem, right? Because you have 200 packets coming in, but I can only service 100, right? Same problem as waiting at in a bank and then or a supermarket, and there aren't enough people serving you, and the line keeps growing. So if this happens, what will happen is this buffer will get full, and when the router buffer gets full, what do you think the router does? Yeah, it starts dropping packets. Typical behavior is, can't handle it. My memory allocated space is full. I start dropping stuff off, right? So when your router starts dropping stuff off, TCP will kick into gear. What will TCP do? I'm sending stuff, and what will TCP see? Yes, so it'll go, I send something, got nothing back, timeout. And what happens in a timeout? You retransmit, and then what happens? This guy's still full, I can't handle it. What happens to those packets? They keep dropping, and then TCP kicks into gear. Keep retransmitting, right? So things just get worse, right? And worse and worse and worse. So you want to avoid that, yeah? Because you're not helping by putting more stuff into the network when the network is congested and full. So how do we manage those situations? This is tricky. Can TCP see that the problem is the router? No. What does it see? What does your transport layer see? All it sees is, sorry? Nothing is coming back, right? I'm sending stuff, nothing, I don't know why, right? I can only guess. Corrupt packet, lost packet, who knows why? Broken, I don't know. Broken link, no idea, right? So my visibility in the network is, I have no idea, right? So this gets tricky. TCP has to find a way to determine that it might be because of congestion. Is it congestion? Then if it is congestion, what to do, right? So this is the same problem as, not the same, kind of the same problem as RTT. How do I estimate a good round trip time when all I'm seeing is I'm sending stuff, not getting anything back, right? Why would that be? Right? No idea, okay? So this is kind of tricky problem to solve, yeah? So these two graphs are directly from the lecture, the book. And what you see here is, so assume that your arrival rate is increasing, and so here is your capacity over 2. What is this graph? So yeah, so this is your service rate, and this is your incoming rate, just like the figure that we had before. So in a link. So eventually, your arrival rate is going to hit, you're going to max out, right? So essentially, how many packets you can service is over here, right? So even if your arrival rate was to increase beyond your ability to service packets, what happens is that your buffer, that means essentially, if when you hit this point, your buffers are already full, I can't service anymore. And then what happens to delay, right? The delay is going to go exponentially, right, at that point. Yeah. Okay. So as you increase the arrival rate, if your service rate, right, can't go beyond this point because that's a max, that's the best I can do as this router, what happens to packet delay? Packet delay is going to increase. Basically, it's going to go to infinity, right? Because I can't service anymore. Okay. So that's what this is trying to say. Yeah. So the way, the reason for that is because essentially what routers do is they just drop stuff. And you drop stuff, that means your delay is infinite, right? Could happen forever, right? Is that clear? What happens? Yeah? Okay, so how do we deal with this problem? A couple of ways to deal with the problem. One is, so one approach is to use what's called network assisted and end-to-end assisted. So when kind of the internet was built, how do you say, the stuff in the middle was very intelligent, right? Because the end systems are like telephones or kind of quite dumb. And so one way, but as time goes by, what you don't want to do is to actually load up the things like routers and switches because they have to route packets and do other stuff, which we'll see in a minute. But you can get the network devices like routers to provide feedback regarding congestion. That's one way to deal with it. And there's a protocol called Extended Congestion Notification, ECN, right? Which we're not going to cover, right? Which is being used, where routers actually notify by modifying the ACK packets to say, look, I'm congested. But the way that TCP works is by using end-to-end systems to manage congestion, right? So this is what we're going to look at in terms of how TCP does it. So this is kind of tricky because if you use the network layer devices, they have a better idea that it is congestion because they can monitor themselves, right, and understand what's going on internally. But if you use end systems, what I mean is two hosts communicating, we can't see what's happening on the routers. It gets a little trickier, okay? So what that means is that if you use this method, which we inevitably going to lead to incorrect inference of congestion because we don't know why our packets are not getting through, right? But if you do network layer, we make the network layer, which we'll see next, that means the routers and stuff more complex. That means they're going to be a little bit slower, but they have a good view of if it is congestion or not, right? But TCP does this, and this gets tricky because it has to guess, right, if it is congestion and work on that, okay? So it can get it wrong. So open question as to how well we can do this. So here's the way that TCP, so we're going to look at like the simplest protocol for congestion. Have I finished time? No, yes. So we're going to look at the simplest protocol for TCP congestion avoidance. And it's called Tahoe, right? So we'll start with this. Now, there are so many different varieties of congestion management or avoidance because it is an open problem, simply because you just don't know how to infer well what is going on in the network simply by looking at the behavior of free transmissions and acknowledgements, which is what TCP sees, right? And timeout events, okay? So based on those events, TCP has to determine what might be going on between two hosts, right? So this is tricky. So remember this guy? Receive window size. What's that used for? What have you used the receive window size for from the sender?
Select for page.
Sorry?
Selecting for page has a window size.
No, remember receive window size in the TCP protocol? What's that used for? Huh? Sorry, flow control, that's right. So this is, so you, as a sender, I need to think about how much data I can send. So I maintain a state which tells me how much space the receiver can handle, right? So this guy comes from flow control. So here's what's new, right? So in terms of managed congestion, we introduce a new state, which is congestion window, right? When I look at exam papers, this is a common confusion, right? That students get confused with the purpose of these two state variables, right? So if you're confused, please come and have a chat with me. So this is for flow control, right? To monitor how much space the receiver has. This is about monitoring congestion, right? So this state variable is to monitor and control traffic flow based on congestion, right? So what the receiver will do is it will try to determine how much pipelining or how many packets are put in the network, right, link, by finding the minimum of these two, right? That makes sense, right? Because sometimes you may find that the receiver has a large amount of space, but hey, it's congested, so I shouldn't be sending that many packets. Sometimes you may find that the congestion is none, right? This is like, really large, but the receiver can't handle any packets. So you got, in terms of determining how many packets to pipeline, you got to find the minimum of these two, right? Okay, that determines how many packets I should send down the link, a minimum of these two, right? So I haven't told you how this value is determined. So this is how that value is determined. That is, how many packets can I send down my link, right? Okay. So initially, you set the congestion window size to 1, or 1 maximum segment size. So this could be in terms of bytes, by the way. So maybe 1,460 bytes. Example, right? So however many bytes, right, is a maximum segment size. Then you set a threshold value. Notice the threshold value is 65,535, and so bytes and 2 to the power, what is 65,535? Does anyone know? 2 to the power, guess. This number is slightly significant. 2 to the power 16. And why is the threshold set to 2 to the power 16? If you notice here, so this is you notice that in terms of number of sequence number space is, so this is 2 to the power 32. So it's half the sequence number space, right, is your window size. Yeah? So you know the relationship between window size and sequence numbers now, right? Sender and receiver. So this is like selective repeat, TCP, right? So it's set to half the maximum possible sequence numbers, right? Is your window size, okay? So while the congestion window is less than this threshold, right? So which is the maximum amount of packets that I'm going to send. What I'm going to do is I'm going to send a single packet, and if I get an ACK for that packet, I'm going to increase my congestion window by 1 maximum segment size. Okay, so I'm going to keep doing this until I hit my maximum threshold of bytes, right? So initially what will happen is you'll send 1 packet, you get 1 ACK back, right? So then your congestion window becomes 2, right? So yeah, so then you would send 2 packets, you get 2x back, your congestion window becomes 4, right? You send 4 packets, you get 4x back, your congestion window becomes 8. You send 8 packets, you get 8x back, your congestion window becomes 16. You send 16 packets, you get 16x back. You get the idea, right? 32. So you essentially end up doubling, right? Okay, your window size. So we're going to continue to do that, saying, look, things look good. So I'm gonna be a bit bold and double my window size and more and more and more packets, right? But if a timeout happens, if I find that, oops, one of the packets I didn't get an acknowledgement for, what I'm going to do is I'm going to cut my threshold value that I set here to half of the smaller of these two values, whether it's determined by flow control or congestion window, and I'm going to set my congestion window to 1, right? So this is quite dramatic, right? You can see that I may be at 32, and if I get a timeout for a packet that I send when my congestion window is 32 maximum segments, and then what I'm going to do is I'm going to jump back down to 1 on a timeout, okay? That means I'm going to send 1 packet at a time again, right? So a bit of a drastic action for a timeout, okay? Because what TCP thinks is the reason I had a timeout was because, I don't know, my best guess is the network is congested, right? Right? My best guess is the network is congested. So if it's congested, there's no point trying to send a large number of packets, right? I'm going to go back down and start slowly again, okay? So this is 1, this is 2. So what happens if the congestion window goes above the threshold? So if I go above the threshold, then I go into what's called congestion avoidance mode, right? What I think is like, what I'm thinking is, so I've increased my congestion window size to a very large number, but based on my previous experience, right? Remember the previous experience may come from a timeout, because timeout determines the threshold, right? Based on my previous experience, I know that if I hit this limit, right, things start to go bad, right? Because remember, a timeout causes a threshold to be updated, right? Okay? So what I'm going to do is, now I'm going to actually increase my congestion window much more slowly, right? In fact, I'm going to increase my congestion window by 1 at a time, right? So each act would increase my congestion window by 1. So this formula here essentially turns out to be increasing it by 1. So to give you an example, if you have a congestion window size, if your congestion window is equal, let's say, 115,000 bytes, and let's say your maximum segment size is equal to 1,500 bytes. So what this would do is essentially give you 1/10 of maximum segment size, right? Okay, so if you're sending 10 segments, that means when you get 10 acts, you increase your congestion window by 1, right? Okay, so what I'm doing is that every time that I send my congestion window, that means pipeline this much data, and I get my acts back, then I increase my congestion window by 1, okay? Right. This is as opposed to doubling earlier, right? Okay, how did I get 10? You guys asking me how did I get 10? Because maximum segment size is 10 times the congestion window, right? So that's why I got 10 here, okay? Right. So, but if a timeout occurs, again, while I'm in congestion avoidance mode, I do exactly what I did before, right? Okay, which is I go, whoa, timeout, which means the network must be congested. I don't know. I'm inferring this, right? Cut the threshold into half. Okay, that's what I'm saying is don't go to this level again, right? Because I know that if my threshold is up here, remember that here I double every time, right? So that means I reach a doubled point where I've got congestion. So now I've gone back to this step, which is essentially halving, right? So let's stay here. But if I'm here and I'm still getting congested, whoa, let's jump back down to the next one, right? So that's what I'm doing. I'm going back to how optimistic I am about how much data I can transmit. Okay? Sorry if this is confusing, but I have 51 seconds. I'll go through this again. So this might be easier to understand, guys, right? Okay? So let's go through this slowly. Essentially, I start with 1, okay? Can you guys see? Right. And then what happens, I go into slow start, okay? Please don't get confused with the name. Although it says slow start, the reason why it says slow start is because we're starting with 1, not because this is slow, right? This is actually quite exponential, right? And this might be slower, so the name is a little confusing. And sometimes you see the answers in the exam call this slow. But this is not slow. This is a multiplicative increase, actually, right? But the reason why we call it slow is because we start from 1, okay? So we start from 1, and then you can see we double the window. We send 1, we get an act back. So we send 2